All right, I want to find the area bounded by two functions, and I have this upward facing polynomial function x to the fourth minus 2x, and then I have the function x e to the negative x squared. And one of the things I need to do prior to really getting into the problem is to find the intersection of these two curves over here. So clearly they intersect at x equals 0. Just plug in 0 into either of these for x and you get 0 for y. So my intersections are 0 over here on the left, and then some unknown quantity over here on the right. So you can't solve this equation analytically. So if I'm trying to find an intersection using algebra, I'm stuck. So I write down x to the fourth minus 2x equals x e to the negative x squared. I have no idea what x is, so we're going to have to use an approximation on this. And what I decided to do in this case is use a TI-84 emulator because I just want to show a variety of different methods as I make these videos. So I plugged in both curves, and then the function that's in the TI that's going to help you is the intersect function. So if I look at a graph of the two curves, it looks about the same as what you see on my my drawing screen. And then I go second function trace, and then click down to intersects, and hit enter on this. It says first curve, second curve, and then it wants a guess for where to start. Now I was already messing with this before I recorded this. It was originally going to give me x equals 0, and I had to give it a better guess for where to look for the intersection. So I told it x equals 1 is the starting point I want you to use. So it thinks for a while, and then it spits out x equals 1.2977 and so on. So 1.298 is what we're going to keep for that. All right, then I want to get into doing this integral symbolically. I was asked to actually show that. So show the calculus there for the symbolic integration, and then we'll plug in this limit and get our approximate area. So I want to visualize an area element, a thin rectangle sliced out of this thing. That's a little dA, a little differential contribution to the area. That's dA. And the height of this thing, so the distance from here to here, is given by the difference in y coordinates, starting with the one that's highest up. So that's the exponential curve. So I have a height of x e to the negative x squared minus the quantity x to the fourth minus 2x. And then my width for my little rectangle is a little dx. Now I can go ahead and write down that dA is equal to the length times the width, or height times width if you want to say it that way. And I get x e to the negative x squared. I'm going to distribute the minus sign just to clean things up. And I get plus 2x minus x to the fourth. That's the height. Then you multiply by the width to get the area. Now we're going to add up all the area. That's all an integral is. So I have the sum of all the dAs. So use an integral sign for the sum. Plug in all your dAs. X e to the negative x squared plus 2x minus x to the fourth dx as x goes from 0 to 1.298. And now I've got to get into symbolically integrating each piece. So if you want, you could break it apart into 3 integrals. I don't want to spend a bunch of time writing the limits on every single one of them, so I know those limits are there. I'm just going to break it into 2 integrals, since really it's just that exponential piece that requires special treatment. And to do this exponential piece, I need the derivative of that exponent right next to e to the negative x squared. So the derivative is negative 2x. So I'm going to put a factor of negative 2 on the interior, negative 1/2 on the exterior to compensate for that. Now this is an informal u substitution, is really what I just did. I'm trying to set it up to recognize the chain rule backwards. You could always use a formal u substitution with u equals negative x squared if you prefer. So I get negative 1/2 times the antiderivative of this piece. So that's just going to be e to the negative x squared. And if you don't believe me, just differentiate that and you'll get back that integrand that we started with. The other piece is 2x. That integrates to x squared. Negative x to the fourth goes to negative 1/5 x to the fifth. And then I'm evaluating the whole thing from 0 to 1.298. Okay, just double checking something real quick. I think we're cool. When I plug in my lower limit, I don't get 0. So there's so many examples where we do get 0. These two terms are 0, but this one, e to the 0 is 1. So I end up, my lower limit gives me negative 1/2. When I subtract that, I'll get a plus 1/2. So I'll get there in a minute. I was just checking to see if I could cut some work out. Okay, so I have negative 1/2 e to the negative 1.298 all squared plus 1.298 all squared minus 1/5 1.298 to the 5th, and then I subtract what I get when I plug in the lower limit minus negative 1/2, so I end up with plus 1/2. So I get an area approximately equal to 1.355. And I should check that this is reasonable over here on the graph. Every one of these squares is one square unit. And if I look at the shaded area here, it seems very plausible. It's just slightly bigger than the area of one of those squares. So that helps to increase my confidence with the answer.